remember, the standard form of a quadratic is ax squared plus bx plus c. One of the main reasons quadratics are worth learning is because how gravity works. Gravity is a quadratic relation. So this formula here is the quadratic formula you can use to model gravity. A is the acceleration. Well, first of all, y stands for your height, and t stands for your time. But from there, this 1/2 times a is kind of like the a value of our quadratic. This v naught, when you have a v, a little circle down there as a subscript, we call it v naught. N-A-U-G-H-T, v naught. That is your initial velocity. That's basically your v value. And then y naught, which sounds like a question. Y naught is your starting height. So there's a lot of components. There's gravity pulling it down for the a value. There's a starting velocity for a b value. And there's a starting height for a c value. And with those components, we can create a formula or an equation to model some gravity. So for this first problem, the acceleration due to gravity when working with feet is -32 feet per second squared. If a model rocket is launched from the ground with an initial velocity of 200 feet per second, write the equation that can model the height of the rocket over time. Well, this -32 feet per second squared is the acceleration. So I'm going to plug that in for the a value in the formula. I'm going to plug that in right here. So I get y equals -1/2 times -32 t squared, t for time. The initial velocity of 200, that's my v naught. That's the initial velocity. So it's plus 200 t. And since it's starting from the ground, my starting height, y naught, is actually 0. I'm 0 feet off the ground. That can simplify to -16 t squared plus 200 t. Now, grab the new calculator program. Hopefully it'll work better than the last one. There. Perfect. So I'm going to start by plugging this equation into my calculator. In the y equals menu, if you don't have a calculator, you can borrow one of mine, of course. In the y equals menu, we do -16x squared plus 200x, and that's it. I don't need the plus 0. X and t are the same thing. So in the y equals menu, I have -16x squared plus 200x. I'm going to jump over to my table. Second graph pulls up the table. And yours might be set to scroll, or it might be set to plug in some numbers. I'm just going to plug in like 0, 2, 4, and just sort of see what happens. Just getting an idea of what's going on right now. What does x stand for? Like, what type of unit is it? It's time. X is our seconds. So it's really our t. Our t value is time, it's seconds. This is 0 seconds, 2 seconds, 4 seconds. What does y stand for? The height in feet of the rocket. So it's saying after 0 seconds, the rocket was 0 feet high, which makes sense. We haven't done anything, it's on the ground. After 6 seconds, the rocket was 624 feet high. After 12 seconds, the rocket was 96 feet high. I'm going to keep going. I'm going to plug in a 13. And that gives me a negative number. I can't have a negative. I'm not going into the Earth. I'm not going below the ground. So I know that this rocket hits the ground after 12 seconds. So on my x-axis on my graph, I'm going to count from 0 to 12. And that's my x-axis is time, and that's in seconds. How high should I go on the y-axis? Where should I start and how high should I go?
Well, you have to go to 624.
I have to go to at least 624, because that's the highest. So I'm going to go to like 650, just to go above it a little bit. So I'm going to count from 0 to 650. If I go by 50s, there's 100, 200, 300, 400, 500, 600, 700, so that's perfect. Go from 0 and count by 50s, so every other space is 100. And I'm going to use the table that I just created. And with the table, I've got a whole bunch of points I can graph. So I'm going to graph all those points. I have 0, 0. I have 0, 0. I have 2, 336, which I'm just going to eyeball as best I can about there. 4, 544. 544 is going to be like here. Right beneath 550. 6, 624. 8, 576. 10, 400. And 1296. I know that by the time I hit 13, I'm hitting the ground. I'm going to draw parabola as best I can. Not perfect, but that's okay. Better than that. That's better. Anybody not any issues with the calculators on this? Okay, I'm also going to get the graph on my calculators to see it. If I just press graph right now, it doesn't look very good. I've got to change my window. I'm going to have my window, have my x values on my window do the exact same as the x values on my graph. I'm going to go from 0 to 14 and count by ones. On the y-axis, I'm going to go from 0 to 700 and count by 50s. So whatever I did over here on my paper, I'm going to have the same window to look at on my calculator. And there's a nice, pretty little graph. So that is the window right there. Are we doing okay so far? If you have any issues, you gotta let me know. Okay. How can we find how high the rocket is after 6 seconds?
Plug in 6 for T.
Plug in 6 for T, because that's our time. I'm just going to plug 6 in for T. And the nice thing is, we've actually already found that point. If I just pull up my table, it was the point 6, 624. So you're just plugging stuff in for x and solving for y on that part. After 6 seconds, the rocket is 624 feet high. How can I find when the rocket is 250 feet high?
Set from
Yeah, 250 is a height. I know height is y. So I'm plugging 250 in for y, and I'm going to solve for x. How do I do that? Mm-hmm. Then what? I could. That would work, actually. That'd be all right. But even then, we're still going to have to do something else. Yeah? Yeah. It's quadratic formula, this. Factoring's not going to work. Including the square would work, but we want decimals anyways. I don't want those radicals. Dividing by negative 16 would be okay. That would give us a decimal here or here. It's just not going to be prettier. The whole numbers are nice. So I'm going to do the quadratic formula in my calculator. Now, you might already have that programmed in there, and that's wonderful. But we talked about how to do this all last class. We do negative b, which is negative 200, plus square root of 200 squared minus 4 times a times c, all divided by 2a. If that 2a isn't in parentheses, it's going to be wrong. Okay, you got to divide by 2a in parentheses. Notice how I had 2 open brackets to start and 2 closed brackets to finish. Hit enter. One of my solutions is 1.41 seconds. If I look at the graph, 250 is here. So that makes sense, it's at about 1.41. My graph's not very accurate, but it's drawn by hand. That's a reasonable number. Now I can hit second enter, change this plus to a minus, I get 11.1. Is that what y'all are getting? Is that okay?
Yeah.
How come there's 2 solutions? Yeah? But we're not trying to find 0. I'm not worried about hitting the ground, though. It's not the question I'm asking.
Because the rocket is at that height at 2 points when it's going up and then it's coming back to the Earth.
Right, it hits 250 on the way up, and then again on the way down. It happens twice. I'm not worried about 0, I'm worried about 250 here. It makes sense there'd be 2 solutions because the rocket hits 250 twice. Okay, how can we find when the rocket reaches its maximum height? How can I find when the rocket reaches the maximum height? Yeah? We're trying to find the vertex. If you're talking about the maximum height, you're talking about the vertex, which is going to be somewhere in here. How do I find the vertex? Matt, keep going. Good. X equals negative b over 2a. Which in this case is negative 200 over negative 32, which is 6.5. Hold on. 6.25. After 6.25 seconds, the rocket hits its highest point. Next, the next part says, how can we find how high it was? We know when it hit the highest point. We're going to find how high it was. Head down. Plug this in for x. Plug 6.25 in for x. Awesome, 6.25.
Oh, it's negative 6?
No, it's positive. I'm going to fix that. And you can do that on your table, which is so very nice. 625 feet. So, after 6.25 seconds, the rocket is 625 feet high.
And how did you know to plug in 6.25 in?
Well, the vertex has 2 bits of information. The coordinate has an x and a y. I found the x first by doing the AOS, the negative b over 2a. I still needed the y value. I get that by plugging in the x. This gives me both a time and a height. Last part, F. How can we find when the rocket hits the ground?
Plug 0 in for y.
Plug 0 in for y. How come?
Because that's how you get the two equations from 0 to.
But why is 0?
That's when there's no height.
There's no height. You hit the ground, your height is 0. You hit the ground. So I'm going to do the quadratic formula here. And luckily, this is what's also really nice about your calculator. I can go back and edit my first equation and just change the negative 250s to zeros. And one of them, just change the negative 250s to zeros, and then change the minus to a plus. Here's the other one. It happens at 0 seconds and 12.5 seconds. Goodness. Well, the first one makes perfect sense. We hit the ground when we started on the ground, so after 0 seconds we're going to hit the ground. The second one, remember, if this is 6.25 and we're symmetric, the next one's going to be 12.5. The problem is symmetric. Is there a question about that problem at all? It's everything we've been doing just specifically for this application. This is where we want decimals instead of simplified radicals. Do the same thing for a new problem. Back page. A kid throws a tennis ball off his roof. He throws it with an initial upward velocity of 8 meters per second from an initial height of 9 meters. And the acceleration due to gravity is negative 9.8 meters per second squared. Part A asks, why is the acceleration due to gravity different in this problem compared to the others? And the last one was negative 32. Here it's negative 9.8. Why is it different? What's lighter? Gravity's going to pull at the same rate no matter how heavy it is. That was a good idea, though. Yeah, Matt?
Its initial height is different.
Gravity's going to pull at the same rate no matter how high you are. It affects, because these are so close to each other, 9 meters and no meters, that's not going to make a difference. There's equations to worry for that, but that's not what this is. The initial height isn't making a difference. Yeah?
The acceleration is different.
Why?
Right now, it's different.
And Alan?
This one's dropping it.
Gravity's pulling everything at the same rate, no matter what we do. If I jump or stand or run or start higher or start lower, it's still pulling things at the same rate. Yeah?
It's the same.
It's not. It was negative 32 last time. This time it's negative
Wasn't that
9.8.
feet, though?
Huh?
Wasn't that feet?
That's the difference. Feet and meters. We're in meters this time. That's the difference. Okay, we're in meters. Yeah? No, it's because we're in meters. The thing I just said 3 times. Yeah, you went like this.
Exactly.
It's different because we're in meters, not in feet. Okay. Take a second and try and write the equation on your own. I'm going to flip to the back side and see what the form is. But take a second and try and write the equation on your own. You don't have to do f of x or f of t, but I'm going to. Hopefully you get something like this. Okay, for part C, I'm going to graph the equation. So my y equals negative. I have negative 4.9 squared, 4.9x squared, plus 8x, plus 9. And I'm going to go to my table. And I can see pretty quick, just from my old numbers, that after 4 seconds, we're already underground. We're at negative 37. So 4 seconds is too fast. So 0, 1, 2, 3, 4. Even at 3 seconds, I'm underground. So I'm going to count from 0 to 3. I think I'll count by quarters. There's 0, 1 quarter, 1 half, 3 quarters, 1, 1, 2, 3, 4, 2, 1, 2, 3, 4, 3. Which makes this a half, and this 1.5, and this 2.5. These are my seconds. How high does this ball go? What I can see on here anyways, at least from the picture I have, from the points I have up here, how high does the ball go? 12.1 is the highest thing I have here, so I'm going to count, this grid goes to 14, so I'm just going to count by ones. 2, 4, 6, 8, 10, 12, 14, and this is the height in meters, not in feet. Well, I'll make my window, my x value is going to go from 0 to 3, counting by 0.5, I guess is fine. My y values go from 0 to 14, counting by ones. And there's my parabola. When does the ball reach its highest point? Vertex. How do I find the vertex, Tyler?
Negative 0, 0.
In this case, it's going to be negative 8 over negative 9.8. .82 seconds. How high is that highest point? How do I find that? Yeah? I'm going to plug 0.82 in for x. And again, I love my graphing calculator. Stop doing that though. 12.27 feet. Okay, will you look up here? Just watch this. If I have a good graph, if my graph looks the way that I want it to, if I can see everything I'm looking for, if I hit second trace, that pulls up my calculate menu. There's a lot of useful things here, and I've shown some before. What I'm looking for is the maximum, the highest point. So if I switch down to maximum and hit enter, and slide that little spider over to the left of the maximum, like about there-ish, and then slide it to the right of the maximum, right about there-ish, and hit enter. Ignore what it says guess, hit enter one more time. Oh, x is 0.82, y is 12.3. You can find your vertex right there, x and y. Follow that, Emily?
Yeah, but I don't have that thing.
Oh, then your window was off. Gotta change your window. What do you think
You kept it on.
minimum does? What does this one do? It tells you the lowest value your graph is going to hit. Our graph doesn't have a lowest value. It's pointing down forever. So minimum is of no use to us here. But if the graph is pointing up, then it would be of use to us. 0 gives you the roots. Gives you the x-intercepts, the zeros. And value just does what our table does. So anyways, how can I find when the ball will be 5 meters high? For x? How come for x? How come for y?
Why is the height?
Because it's a height. We were given the height, that's a y value. So I say 5 equals negative 4.9x squared plus 200x, or plus 8x plus 9. Now what? Subtract 5 from both sides. Left myself some more room. And that gives me 0. This has to be equal to 0 to work. Now I'm going to do the quadratic formula. I wish I'd programmed something into this calculator. Maybe I will someday. Negative b is going to be negative 8 plus square root of 8 squared minus 4 times a times c, all divided by 2a. One of my solutions is negative 0.4. Back and find the other one. That's a minus 2.03. Now this one doesn't make any sense. Why did it give me a negative solution? Yeah.
Because you never started at that height.
Right, we never started at that height. I never actually graphed this, but the graph looks like this. Not exactly, but kind of like that. If we wanted to have a starting value of 5, it would be here, we would have to go back in time. Well, we're not going back in time. The equation isn't good back in time, so this one's no good to us. We only hit the height of 5 feet once, because we started higher than 5 feet. We started at 9 feet, which makes sense. So that's why there's only one solution, not two. We started higher than 5 feet. How do I find when the ball hits the ground? It's like zeroing for y. The height of 0. And if I have a good graph, I can do that by doing second trace to pull up calc, scroll down to 0, have one spider on the left side of the 0. I'm looking at the 0 down here where it's kind of off screen. I'm going to scroll all the way to the right side of it, which is going to take forever. now I can see that the y value is negative. If I look at the y value here, it's negative, and that's what I want. I want to go from a positive y to a negative y, hit enter, and enter again. It happens at 2.4 seconds. Right after we had a thing of 5 meters. All right, is there any question about that? Good. It's nothing new. It's vertices, vertices, I guess I should say. Quadratic formulas, plugging things in for x, plugging things in for y.